Hello, greetings, and welcome. Let's take a look at our second critical path example um, problem from Chapter 7. So, a publisher has a contract with an author to publish a textbook. The author submits a hard copy and a computer file of the manuscript. The simplified activities associated with the production of the textbook are summarized in the table below. Use the forward pass to calculate the earliest possible starting and finishing times of all activities. Use the backward pass to calculate the latest allowable starting and finishing times of all activities, calculate the total floats of all activities, and then determine the critical path. So I'm going to take this problem in two parts. So first, I am going to set up a network based on columns 1 and 2 are activities, and then the precedence of our activities. So I'll set up a simple network in which each activity is a node. So it'll look like a network as we've seen them in the past. And then once I have that and I have all the connections right, I'll then rewrite it using the suggestion of the textbook, where I replace each node with their 3x3 table, in which in row 1 we'll list the earliest possible starting and finishing times, so what we're asked in the first part. The third row will correspond to the latest possible starting and finishing times. Then in the second row, in the middle, we'll have the activity, and then to the right of it, we'll calculate the float, which we can then use to determine our critical path. Okay. So eventually, once we get good, we could probably skip this first step of drawing the network. But for me, it's an extra step that requires a little work, but helps me in terms of making sure I get all the connections and that everything is right. Okay, so when I construct this network, I'm going to start with some initial starting node. Okay, and the duration of that starting node is going to be 0, but then this way I tie up any sort of loose connections, if you will, in this network, so that my network starts and ends at a single point. Okay, all right. So I'm gonna have some starting node. Then when I look, I see A, B, C, and D have no precedence. Okay, so I'm gonna have I'm gonna draw a node A, B, C, and D. Okay, and I'm gonna connect all of them to this initial starting node. Okay, so basically what this tells me is that I can start with tasks A, B, C, and D. Okay, so right off the bat, I can start with any one of those tasks. Then when I look at E, activity E is dependent on A and B. Okay, so activity E is going to be dependent on A and B. F is dependent on E. G is dependent on F. So it's like I have this initial phase in which I can choose any of the tasks. Now I have these tasks that need to be completed in series. So G is dependent on F. Now we have H, which is dependent on D. So I'm going to draw task H down here, which is dependent on D. I is dependent on G and H. So I'm going to do, say, I over here. And that's going to be dependent on G and H. J is going to be dependent on C and I. So J is going to be dependent on C and I. Okay, so that's the last step. So then I'm going to have my terminal node. Okay, and when I'm going to connect to my terminal node are going to be all of these activities or tasks which otherwise don't, connect to any other terminating node. All right, so J has no terminating connection, so J will connect here. Okay, when I look at all my other ones, G ends with I ends with J, so it looks like everything flows through J. All right, everything ultimately flows through J, which is going to end in this terminal node. Okay, so now when I've drawn it out this way, I'm going to need a little more space than I originally thought, or maybe I can rearrange my network in a slightly different fashion, right? So in theory, maybe I turn it upside down, but I guess it doesn't really matter. Okay. So I'm going to have some starting node, okay, NS, okay, and then I'm just going to draw out my grids for A, B, C, and D. Okay, we had A, and then I'll draw the connections in last. C. Oh, shoot, I'm off the page. So let's see, well, let's have to squeeze D in here, I guess. We can do it since they're all in parallel. It's okay. So there's A, B, C, and D. Okay, then I'm going to draw E and H. I kind of have this set up in columns. So I'm going to have E here. E, H, hopefully the more and more we do these, our drawing gets better. Here I'm just kind of cut off, right? Ideally I would have rolled into the next page, I suppose. So there's E and H. Then we had F. G. I drew that one pretty small. Actually, we could move G to save space, but it doesn't really matter. So G. Okay. Okay, I'm going to put, say, I down here, though, in the interest of space. Then I'm going to have J. I can't remember what's connected to J. We're going to have a couple things connected to J. So let's move J off a little bit. Let's say put J here, because then J is just going to connect to my terminal node. Okay, and we'll have our terminal node. Bam. All right, so my starting node can go to A, B, C, or D. B, C, or D. Then A and B connect to E. C connects all the way to J. D connects to H. And then we had E to F, F to G, G to I to J, I to J, H to I, with I then going to J. Okay, and then J goes to our terminal node. Okay, so I think that's everything. Okay, and so next I want to add the durations to my chart. So this is, time in weeks. So A is 3 and B is 2. A is 3, so I'm going to write it in this middle column. B is 2. So A is 3, B is 2. Then C and D are 4 and 3. E is 2 and F is 4. Okay, G is 2 and H is 1. Okay, G is 2 and H is 1. I is 2 and J is 4. I is 2 and J is 4. Okay, so now I'm going to change my color to red. We're going to go through and we're going to do our forward pass and determine the earliest possible starting and finishing times. Okay, and in that process, we will also determine the time to complete our process. And so when we do our forward pass, right, I'm going to initialize my starting node at time equals 0. Okay, and then I'm going to move forward through my network. Okay, so for my starting node, I go to A, B, C, and D. Okay, so the earliest possible starting time for A is going to be 0. Its duration is 3. And so its earliest possible finishing time is 3. For B, I start at 0. Duration is 2. So I'll finish at 2. C, start at 0. Duration of 4. Earliest possible finishing time is 4. D, start at 0. Duration of 3. Earliest possible finishing time is 3. Okay. Alright, so then as I proceed through my network, let's look at E. Okay, so E has a precedence of A and B. Okay, so before I can move on to E, I need to complete A and B. Okay, so what I'm going to look at is I'm going to look at the earliest possible finishing time, okay, of my I'm going to look at the earliest possible finishing time of all precedence activities, and I'm going to find the maximum value because that's going to be my earliest possible starting time. So when I look at A and B, so I have 3 and 2, so the earliest possible starting time of E is going to be 3. All right, so if it can't start until both A and B are complete, I'm going to be held up by the process that is going to finish the latest. Okay, so the earliest possible starting time of E is going to be 3, has a duration of 2, so its earliest possible finishing time will be 5. If I keep going this way, F just has a precedence of E, so its earliest possible starting time will be 5, duration of 4, so earliest possible finishing time will be 9. If I go to G, which just has a precedence of F, its earliest possible starting time will be 9, has a duration of 2, so its earliest possible finishing time will be 11. If I look at, I is going to have 2, so let me jump down to H. Okay, H just has a precedence of D, so its earliest possible starting time will be 3, has a duration of 1, so its earliest possible finishing time will be 4. So now when I look at I, okay, I has a precedence of both G and H. Okay, so I'm going to look at the earliest possible finishing times for all precedents, which in this case is G and H, and the maximum value is going to be my earliest possible starting time. So when I look at G, its earliest possible finishing time is 11. H, its earliest possible finishing time is 4. So the earliest possible starting time of I is 11, has a duration of 2, so its earliest possible finishing time is 13. Okay, so then if I go to J, J has a precedence of I and C. Earliest possible finishing time of C is 4. I is 13. So the earliest possible starting time for J is 13. Has a duration of 4. So its earliest possible finishing time is 17. Okay. Then that takes me to my terminal node. Okay. And so we find then that it's going to take 17 weeks to complete the project. Okay. So this is going to take 17 weeks. All right. So now what I'm going to do is a backward sweep in which I determine the latest possible starting and finishing times of each activity in order for this project to be completed in 17 weeks. Okay. So for my terminal node, all right, I just have one connection, and that's to J. Okay. So the latest possible finishing time of activity J is going to be 17. Okay. And so it has a duration of 4. So the latest possible starting time of J is 13. Okay, and then let's move backwards. So if I look at I, okay, I is only dependent on J. Okay, so going backwards, so J is, how do I say this? I is going backwards. I is going to follow J. Okay, so if the latest possible starting time of J is 13, then the latest possible starting time of I is going to be 13, has a duration of 2, so the latest possible starting time is 11. All right, so basically I needs to begin by week 11 and end at week 13 in order for J to begin on week 13 so it can end in week 17 so we can complete this project in 17 weeks. Also looking backwards from J, J is connected to C. Okay, so C needs to be completed before J. So the latest possible finishing time for C is 13, right, in order for J to start on week 13 and complete on time. It has a duration of 4, so that means the latest possible starting time of C is 9. Okay, so that takes care of C. Going from, let's go from I to H. Okay, so if the latest possible starting time of I is 11, then the latest possible finishing time of H is 11. Okay, has a duration of 1, so the latest possible starting time of H is 10. Then if we just take that back to D, okay, so H is dependent on D. So if the latest possible starting time of H is 10, the latest possible finishing time of D is 10, has a duration of 3, so the latest possible starting time is 7. So that takes care of that path. So now let's go from I to G. Latest possible starting time for I is 11. So looking backward, so I is dependent on G, so the latest possible finishing time for G is 11, has a duration of 2, so latest possible starting time is 9. Okay, going to F. Okay, so therefore the latest possible finishing time of F is 9, has a duration of 4, so latest possible starting time is 5. Going to E. So therefore the latest possible starting time of E is 5, has a duration of 2, so the latest possible starting time is 3. Okay. Now we've got to look at E and AB. Okay, so E is connected to both A and B. So if the latest possible starting time of E is 3, the latest possible finishing time of A is 3, and it has a duration of 3. So that's going to mean it has a latest possible starting time of 0. B has to have a latest possible finishing time of 3, has a duration of 2, so the latest possible starting time is 1. Okay. All right, so now we need to go and calculate our floats. Let me say write our floats in blue. Okay, so looking at A, so the earliest and latest possible starting times and finishing times are the same, so I have a float of 0. Okay, so that means that this this activity must begin in week 0 and must be completed in week 3 for the project to be completed on time. When I look at B, the earliest possible starting time and latest possible starting time differ by a week, right? And so then you see the finishing times do as well. So this means I have a float of 1 week. So as long as this project or this activity begins between week 0 and week 1, right? I have this 1 week window to begin this project, and for which then the project can still be. So I have a 1 week window in which I can begin this activity, for which the project will still be completed on time. When I look at C, it's even bigger, right? I have a 9 week difference between the earliest and latest possible starting time and then finishing time. So I actually have a float of 9 weeks. So activity C, I have a 9 week window in which that activity can begin in order for the project to finish on time. And for activity D, I have 7 weeks, right? I have a window of 7 weeks over which that activity can begin for this project to be completed on time. Okay, cool. So A has to begin immediately. B, I have flexibility of a week. C, 9 weeks, and D, 7 weeks. Okay, then looking at E, see the earliest and latest possible times are the same. So I have a float of 0. It must begin in week 3 and end in week 5. Same is true with F, a float of 0. That activity must begin on week 5 and must end in week 9. G, I likewise have a float of 0. That activity must begin on week 9 and end on week 11. Same with I, float of 0. J, float of 0. H, difference between my earliest possible starting time and latest possible starting time and earliest possible finishing time, and latest possible finishing time is 7, right? So I have a float of 7. Okay. So my critical activities, okay, the one that there's no window during which that activity could begin, it has to begin at that very specific time. Okay, my critical activities are going to be A, E, F, G, I, and J. So we would say our critical path, so my critical path would be, now I've got to go over to the next page. Where's my cursor? Oh. So my critical path is going to be A, E, F, G, A, E, F, G, I, and J. So those are the activities which must be completed or started and completed on time in order for this project to be completed in 17 weeks, to be completed on time. Any delays in any of those processes or any of those activities, A, E, F, G, I, and J, would lead to a delay in the completion of my project. Okay. However, B, I have flexibility of a week. C, 9 weeks. D, 7, and H, 7 as well. Okay. Cool. So that is example 2. Fun.